Welcome to the Derivatives module. Today we'll study function growth and decay. Prerequisites include knowledge of elementary function derivatives, the derivative definition, and basic math operations. If you've seen our previous videos, you should be well prepared. Let's explore the definition of a function's increase and decrease. We consider a function as increasing over a specific set S, whether it covers the entire line or only a small portion of it. If, for any pair of points labeled as x sub 1 and x sub 2 in set S, where x sub 1 is smaller than x sub 2, it is satisfied that f of x sub 1 is less than or equal to f of x sub 2. In other words, the function value at later points is greater than or equal to the function value at earlier points. Equality is also a possibility in this context. A function is considered strictly increasing when the same rule applies. Take 2 points, x1 and x2, with x2 being larger. At x2, the function value is greater than at x1, and more importantly, it cannot be equal. This means f of x1 is greater than f of x2. Mathematically, this definition might seem complex, but it's straightforward when viewed graphically. If you observe the graph, the function rises from left to right, starting at, let's say, -2, and it ascends continuously. This graph signifies an increasing and, in this case, strictly increasing function. While there might be some ambiguity with certain points when viewed graphically, it's still evident that the function is increasing. Whether or not equality holds in the previous inequality at those specific points is uncertain. When do we label it as decreasing? It's quite similar. We consider 2 consecutive points where one is smaller than the other. If it holds true that f of x1 is greater than or equal to f of x2, then it's considered decreasing. Picture having x1 and x2. If x1 is larger than this one, then the function's value at this point must be less than what it was here. In other words, it goes down. That means a decreasing. Strictly increasing is when there's no equality. It means f of x1 is greater than f of x2. Graphically, it's just as clear. This function is decreasing. Why? Because consider taking -1 and 1 as your x1 and x2. Here, x1 and there, x2. The function's value at x2 is less than at x1. So this function is decreasing at all points, and we can confidently say it's strictly decreasing in this case as well. We're going to examine an important theorem that will teach us how to determine whether a function is increasing or decreasing and pinpoint the intervals in which these behaviors occur. This theorem will be our tool as we dive into the next part of our discussion. If f is increasing in an open interval from a to b, I'm referring to a small part of the real number line. If f is increasing, let's assume it's both increasing and differentiable at every point within that interval. In such a case, the derivative is positive. When the function is increasing, the derivative is positive at every point within that interval. We're discussing a specific interval here. And the reverse is also true. If the derivative is positive, then the function is increasing. The theorem tells us that if the derivative is positive, the function is increasing in that open interval. For decreasing functions, it's the same principle. If f is decreasing, assuming it's differentiable at every point, then the derivative is negative. If the derivative is negative, the function is decreasing. Does that concept make sense? Why do we analyze growth and decay using the first derivative? Let's recap for a moment. In a previous session, you learned about the tangent line. You should also recall that the derivative of the function at a point represents the gradient of the tangent line. It indicates the steepness of the tangent line. Let's take a look at a graph that has made appearances a few times. We're going to draw tangent lines at different points along this graph and observe their behavior. Here's the tangent line and its slope. Pay attention to the slope. When it's positive, the tangent line moves upwards, and when it's negative, the tangent line moves downwards. Let's see how this works. Let's press the play button and you can see how all the tangent lines are represented. But I'm only concerned with the tangent line slope. Clearly, this function is strictly increasing, as evident. Nevertheless, there's a segment here, watch out, where it can indeed decrease. In fact, there's a portion right here where it does decrease. Look at the following. If I focus solely on the function's derivative, which is equivalent to the tangent line slope, it provides valuable information about the function. Let's pause for a moment and consider this point approximately at 3. The tangent line is this. The slope, positive. How is the function at this moment? Increasing. Let's move forward a little bit more. Let's pause the animation here. This is why I could tell it was in a decreasing phase during this period. In a small interval around here, the function exhibits a decline. Why? Because the slope of the tangent line is negative. It points downward. You can observe the slope heading downward. That's the connection between the derivative and the concepts of growth and decline. I examine the tangent line slope. When the slope is positive, it indicates that the function is increasing. When the slope is negative, it indicates that the function is decreasing. What's the process for examining a function's growth and decline? Let's break it down into a few steps. If we understand that the key factor is the function's derivative, our first task is obviously to calculate that derivative. So step 1 is differentiating the function f of x, in other words, calculating f prime of x. Now the second step. We set the derivative equal to 0 and proceed to solve the equation. Why do we set it to 0? It's quite straightforward. What we're essentially doing is identifying when the derivative changes its sign. You have a function, and you know that when a function transitions from being positive to negative, it signifies that it crosses the x-axis, provided it's continuous, which we are assuming it is. So, we take a function and determine when it goes from positive to negative, and this occurs precisely at the points where we set the equation to 0. That's why we equate the derivative to 0 and solve for it to discover the points where the derivative changes sign. Naturally, though I haven't mentioned it explicitly here, we always need to consider the function's domain, so please be careful. Now, on to the third step. We examine the sign of the derivative based on the values we obtained previously, taking the function's domain into account. In essence, we perform a sign analysis of the derivative. This allows us to determine where the derivative is positive, indicating that the function is increasing, and where it is negative, suggesting that the function is decreasing. I find that using examples can be very helpful. Take a polynomial x cubed minus 3x plus 1. We want to determine when the function is increasing and decreasing. The first step is to find the derivative of this function. I hope deriving this function doesn't pose any problem. It's a polynomial, so when we differentiate it, we bring down the exponent, subtract 1 from the exponent, and for the term negative 3x, its derivative is simply negative 3. This results in a polynomial of degree 2. To make it a bit neater, I factored out the common factor of 3, giving us 3 times x squared minus 1. Next step, we set the derivative equal to 0 and proceed to solve. This is straightforward. It's a second degree equation. You can apply the well-known formula, minus b plus minus the square root of b squared minus 4 times c times a, all divided by 2a. Alternatively, you can use other techniques. In this instance, it's relatively simple to identify the points at which the derivative equals 0. So we equal to 0. The 3 is multiplying. It passes to another part dividing. 0 divided by 3 is 0. X squared minus 1, very easy. You have several options. You can pass the minus 1 to the other part. Then I have x squared equals 1. From here, by taking the square root, you find that x is equal to plus minus 1. Clearly, both values are solutions to this equation. I now have the values where the derivative equals 0. The next step is to determine when the derivative is positive or negative. These 2 points divide the real number line into 3 segments or intervals, from negative infinity to minus 1, from minus 1 to 1, and from 1 to positive infinity. All these intervals are open, meaning that none of them includes either 1 or minus 1. They are all considered open intervals. Indeed, at both 1 and minus 1, the derivative is 0, so it's neither positive nor negative at these points. Therefore, we consider the 3 open intervals, from negative infinity to minus 1, between minus 1 and from 1 to positive infinity. Let's determine the sign of the derivative in each of these intervals. It remains constant within each interval. Either it's positive or it's negative. How do we do it? Pick any value from each interval, it doesn't matter which one, and substitute it into the derivative. This will show us whether the derivative is positive or negative. I've chosen the following values. For the first interval, from negative infinity to minus 1, I selected minus 2. In the interval from minus 1 to 1, I went with 0. And for the third interval, from 1 to positive infinity, I chose 2. Aim to use the simplest values whenever possible. What happens? For the first interval, between minus infinity and minus 1, I chose the value of minus 2. When I calculate the derivative with minus 2, I get 3 times minus 2 squared minus 1. So this simplifies to 3 times 4 minus 1, which equals 3 times 3, resulting in a positive value. This means the derivative is positive in this interval. Now, when I substitute 0 into the derivative for the second interval between minus 1 and 1, I have 3 times 0 squared minus 1. Please note there is a small mistake here. The result should be minus 3. What's important is that this value is negative, indicating that the function is decreasing in this interval. And lastly, what's the value of the derivative at 2? When I substitute 2 into the derivative, I get 3 times 2 squared minus 1, which simplifies to 9 once more, indicating a positive derivative. In the third interval, the derivative is positive. The function is increasing. In summary, the function is increasing in the interval from negative infinity to minus 1, decreasing in the interval from minus 1 to 1, and increasing again in the interval from 1 to positive infinity. A note. I mentioned this earlier, but I'd like to emphasize it once more. In this particular case, the function is a polynomial, and it's continuous at all points without any issues. Its domain includes all real numbers. By splitting the line into 3 segments, I've effectively divided it into the necessary intervals. There's no need to create additional subdivisions or subintervals. However, it's possible for the function to be undefined at certain points. In such cases, you need to consider this when studying the growth and decline. Why? Because it's possible for the derivative to change sign at a point where the function itself doesn't exist. In such cases, you must proceed with caution or further subdivide the intervals for a more careful analysis. So, up to this point, we've covered the concept of growth and decline, linking it with the derivative, and we've worked through some examples to demonstrate how to determine growth and decline. I trust that all of this has been helpful. Thank you for your attention.